driving an e-tron. So my conclusion is that driving an e-tron is more exciting than going to Disneyland. Is that true?
I would say yes.
Of course he's going to say yes. And Dick, why not next year, instead of everyone going to Disneyland tonight, why don't you just get a bunch of cars here and we'll just cruise around? Yeah? Now you're kind of sorry you said yes.
No, I'm not.
Yeah, as long as we buy them, right? Anyway, Roger, me in?
Yeah, sure.
This is like, you know I'm in automation when I'm carrying 2 pairs of glasses around. It's redundancy. It's 2 for 1 at Home Depot, $5.99. All right, so I want to talk about this from my perspective. Do my best for you, share some ideas. This was the mission statement of this meeting here today. And I really want to talk about, trust and management, because if you can't trust the data, what is your root of trust? What's the point of the data? How do you know that you're analyzing something that's real, right? So that's a key theme in my message. So here's a bunch of, I got the orders wrong here. Sorry, you can tell I copied and pasted this presentation from others because I had the order all wrong. At any rate, so what is the edge? What does it mean relative to the IoT? The term fog is the computation between the edge and the cloud. So what is this foggy edge thing? I try to understand it, and I think that's why we come here and we go to these sessions, because we're all trying to figure this out. Like, what does all this stuff really mean in very practical terms? And what does this mean? We're all, as users, we're always managing legacy, because the rear view mirror is so much more expensive than what's in front of us. How do we take care of this capital infrastructure? And that's very much true in process automation. My focus is process, factory automation, so it's a really balanced message here today. So let's think about that. First of all, also, the cloud is not a place. When we think of the cloud, I'm going to download or upload my pictures to the cloud because we're thinking, because it's going to be something that Apple or Google have. But it's not a place. It's a set of technologies. And so cloud, the function to which you can deploy cloud is really computation, memory, and bandwidth. And so as these things become more ubiquitous and cheaper, then they transport themselves further and further down. And so as these tools become more flexible and more scalable, then the function of cloud, the idea of a cloud, will move wherever it makes most sense. So put a stick diagram together here to try to figure this out. In the process world, the edge, the instrumentation, really, you're measuring temperature, pressure, current, and voltage, and that's almost all of it. And everything else is some derivative or combination of that. Relatively simple. You're actuating either a throttling valve of some kind, 0 to 100%, or an on-off valve, 1 or 0. So if fundamentals are there, measurements are simple, actuation is even simpler, but it's all the goop in the middle. So you see these little pictures, little bubbles. As we will evolve, I think the cloud, the functionality of the cloud, will just be wherever it needs to be. I mean, I can show you, if you were in my lab, I could show you an instrumentation head-end, universal architecture. It's about half the size of a credit card. It has more horsepower than a DCS controller. It has 16 gigabytes of flash, half a gigabyte of DDR memory, and it runs on a few milliamps of power. So why couldn't you execute and store data and other things in every instrument and actuator out there? So we'll see where it goes. But the other important point is there are millions of these devices out there. And how do we empower that? How do we get that data? So what's the amazing thing is that as the process automation architectures evolve over, say, 25 to 30 years, even 40 or 50 years, the instrumentation actuation evolution is much tighter. So you have hundreds of thousands, millions of instruments that have multivariable data through HART and Profibus and DeviceNet and Ethernet, but you can't go anywhere. They're stuck where they are because the process or the system automation instrumentation can't get the data. You can only get it with a handheld, right? So there will be a great, revolution or a great, step forward when you can literally just suck up the data that's already there. So, number one. Number two, how big is that data? Well, certainly, the petaflops and gigabytes and zettabytes and all that, way up there. Let's think about what's going on down here where all of this is supposed to go. So let's say you've got 100,000 instruments out there, which is a modest kind of process industry of some kind. 100,000 instruments, each instrument or actuator, maybe 10 valuable tags of some kind, and 100 bytes, that's a lot, to format the data and put it in an Ethernet package and send it up. That's only 100 megabytes of data, right? I mean, that's nothing across 100,000 instruments. You can process that, and if they're all connected through twisted pair over, the baud rate of HART, you're in good shape. So, getting to where we are, to exploiting that data, and then getting the data and ensuring that you trust that data, because as soon as you get it, it's secure. Then, what are the process analytics that make sense? Let me cite an example. In this controller thing, that's Bedrock. I'm not pitching Bedrock. I just want to be sure. So every once in a while, I'll throw that name out there. But I did you a favor on e-tron, so. Okay. But, I've seen at these shows, and you see them all over the place, the companies that have been born from nothing that say, I have cyber analytics. Here's a chunk of hardware. Here's a bunch of tools. Here's a ton of software. Here's a bunch of training. Here's a bunch of costs. I can give you motion detection and, analytics on the network, etc. All right. So by containing the complexity of that problem where it exists there, we created all these functions. Created an application that does cyber analytics, intrusion detection, denial of service attack, time analytics, in 1,000 lines of C. And it runs in less than a microsecond on an ARM9, and it's free. And so let's get practical about these things, right? And make sure that we put the application and we extract the value at the lowest possible cost. And how to do that is it will take probably 10 to 100 years to get the next generation of actuators and instrumentation, depending on brownfield and greenfield and the real world that we live in. But the first thing that these devices connect to, which upgrade more frequently, the PLCs and the DCSs and the RTUs and others, well, you want to make sure that that is where you can capture that data and that the data remains in its highest possible quality because it is secure. So now let's talk about security. So where should analytics exist? Process analytics, instrumentation analytics, machine analytics. You can do these kinds of things in very simple, fundamental ways with current state-of-the-art technologies. Just put them together in the right way. And so, blah, blah, blah. You can read my slide. But let's get going here. What are the fundamentals of security? It's authentication, data integrity, and confidentiality. Again, you can read my slide. I don't want to be spitting this out for you. You can go to our website and download our white papers, and we explain all this in some detail. But how do you ensure that this is all there? The other very important point is encryption. How strong is the encryption? Because yes, quantum computing at some future decade could potentially unscramble these things, but have you seen the current, state-of-the-art quantum computers? You're not going to be, the average person is not going to be doing these things, and you're not going to be, applying it so long as you do have state-of-the-art cryptography, which is important. Which means if you're going to execute state-of-the-art crypto, you need hardware in silicon that can accelerate this math and ensure that the math gets done in real time. So that's really important, the strength of the crypto and how are you going to execute it. Now, there's basically 30 or more different hardware, software, operating system, semiconductor technologies to build a chip. In our case, our parent company yourself, we spend as much money building a chip that's the size of your fingernail than some companies would invest to build an entire new PLC platform. And it's just on your fingertip, because that's where it starts, right? And there's a bunch of them. We don't have time to go through them, but it's commercially available, state-of-the-art cyber semiconductor technologies available today. Put them all together, but it's really hard to do. So here's the thing. Security as it exists today is going to remain an expensive, difficult problem for the user until the OEMs, the suppliers, bite the bullet and address this expensive, difficult problem so that the problem goes away. This is hard to do, but once you do it once, it's embedded, and the way in which you use and interact with an automation system today in an insecure world needs to be the same way you did it in the past, which means you shouldn't care. Your sons and daughters and children can go to your iPhone or your mobile device and you can teach them how to go buy something on Amazon, or you don't have to teach them and they'll do something accidentally. Now they're sitting on an insecure appliance, doing a financial transaction or over $1 trillion infrastructure to do a public-private key exchange and ensure that your identity and your financial information is secure. So something that's extremely complex was made very simple so that you don't screw it up. Well, that took a lot of work, a lot of money, a lot of people. So the same thing has to happen in automation. You have to be able to just go to that monitor or go to the engineering terminal or go to the device and do what you need to do, knowing that the authentication and the data and the confidentiality exists, right? And then you're not having this conversation anymore. You're not coming to this session, you're coming to some other session. So it starts, as I said, in the silicon. There's very advanced technologies to ensure ultimately that you have secure boot. Just remember, a secure boot. That's what it's all about. That system has to start up regardless of how large the application is in a secure way. So everything has to be encompassed in a monolithic piece of highly specialized semiconductor technology. Now, 10, 15 years ago, you couldn't even get that stuff, and now it's commercially available, and you can put it in a $5 piece of electronics. But it probably took $1 billion or more to get there. So that's a piece of it. These devices have to address legacy. You have dozens of legacy protocols and emergent new protocols for speaking up and down to the network. These are important practical pieces of the puzzle. And this is the hard part. The hard part is there has to be a chain of trust all the way from the programmer, programming firmware, software, applications, the chip, the way it's built, the way it's assembled, the way it's manufactured. You have to have a chain of trust technology that ensures from a die, a 12-inch raw die that goes through 250 different process steps in a fab, and it goes through multiple probes and sensors and packaging and test and retest. Every part and every step of that has to be authenticated and encrypted until you get a chip, and then that chip is assembled on a board, and the assembly house and the test process and the insertion of the firmware, all that stuff is really hard to do. That's my problem to chew on. And as we design this secure platform, it took just as much time and money to design the factory as it did to design the product. So an appliance here is an example. These are device lifecycle management technologies that have been recently used in aviation, aeronautics, and in high-end military missile systems and other very, very high-end technologies. This is available if you use it and you want to build a factory that's building controllers and I/O modules and edge devices of any kind. Again, what happens is a module is birthed. In other words, it's secure at the moment that it's born. And specialized appliances read the serial number that's on the die, hands off, and create, through some complex math, a series of certificates and keys that are then burnt into secure memory, and then the connection between that chip is fried and burnt, and now that chip has firmware, software, certificates, keys, and it knows how to come alive. And it can be started up and shut down, 1,000, 1,000,000 times, and it's stuck in a box. It's like we're all living, we're the bits and bytes inside of a secure chip. That door is closed and we can never get out, right? That's how it works. As a result, security just happens. It's built in. You can authenticate all human computational memory transactions because it's authenticated to a root of trust that's built into the silicon and therefore exists in the module and exists in the application. That's how you do it. There's no other way. That's state of the art. Now, as was alluded by Dick, there's lots of crazy, amazing things going on. In computation, we have central processing units, CPUs. We have graphic processing units, GPUs. And now you have tensor processing units and various derivatives of that everyone in the world is getting into it now. So these all have fairly specialized capabilities. Graphic processing units because they're doing highly specialized vector math. CPUs because you're doing floating point, fixed point. TPUs, you're doing inferential, low resolution, fixed and floating point math, and you're doing gazillions and gazillions of these things. But no matter what that chip is, no matter what kind of chip, if it wasn't designed the right way, because it needs to be secure and has to secure boot, because it has a TPU, because it has crypto accelerators, because it has side protection for electromagnetic side protection attacks, because it's built as a monolithic single ASIC, and it's built in a fab that has built all the process to ensure that when it's in the package and lands at the contract manufacturer, no one has been able to tamper it, then you have a chip that's relevant and real. And it doesn't matter what kind of chip it is. So ARM and Intel are probably much further ahead, especially ARM in the embedded space, because they won that war. But it took 20 years for ARM to really become a de facto standard in the embedded space. So these processors, as they move down, this is in 2019, this Edge TPU, you can get it on a Raspberry Pi. It's a hell of a journey from Raspberry Pi to an instrument out in the field controlling, some kind of a process that can spill or kill. But still, it'll get there. I don't know where this will all end. I know where it can go right now. And I know what it takes to get there. It's important that we focus on the trust and we create the architecture and solve the problem so that all those millions of instruments and all those thousands of engineers can go to work and just work on that system and make it do what it's supposed to do like it always did. So, summary. Cloud technologies are moving to the edge. I can build you an instrument today, a valve that's got more horsepower than a state-of-the-art DCS controller and runs containers and can run 1,000 PID loops in it at a couple of hundred microseconds and blah, 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 blah. But will it matter? And is it commercially viable? Time will tell. These tools exist, but the market drives it, and we have to think about, in the rearview mirror, how to protect it, and think about how to go forward in the most practical way. Now, I would end this In a little story, if I could, because you said something that was extremely important. It's one of the most important problems to solve in life cycle cost, and that is upgrading, right? So I can demonstrate to you today the technology exists where if it's built right, because the trust is there, because the infrastructure is there, that means that you can transact with your computing embedded machines in the same way that you transact with Amazon or Bank of America, and you know it's going to be secure. And remotely from anywhere in the world over a public zero trust network, you can upgrade an embedded machine, an I/O module or a controller, in real time without ever interrupting the process in minutes, a couple of minutes, and it doesn't matter how many you have. So one of our customers that we're working on chose this technology because that's their vision, because they have over 4,000 PLCs in an upstream oil and gas production environment. And we've proven and demonstrated to them with a single keystroke of a particular engineer that's biometrically authenticated to that environment, and that environment is authenticated and encrypted to the application, to the workstation. The workstation has an encrypted and authenticated tunnel to the controller, and that person, through a two-man rule, or however you define the role-based action, that person presses one button, all 4,000 controllers perform a firmware upgrade simultaneously in under 2 minutes. That is diabolical cost reduction. But whether it's that application or the next or whatever, you can do really cool things if you have security. And if the security is built in and the root of trust is as close to the process as you can get it. That's my message. Thank you very much. Any questions?